Yeah, so my name is Florian Bärtl. Thanks for the introduction. I'm from the High Field Laboratory in Dresden, Germany, and I want to present some of our NMR investigations in the time of the symmetry breaking state of BKFA. So first, let me thank all of the collaborators, most importantly Vadim, who initiated the project, but also Hans Henning and Federico and his group, who provided the resistivity and nonce effect measurements, and of course Igor and Julian, who had done the theory work. So as a very quick outline, I will give a short introduction to BKFA in the whole context of this topic, and then I will talk a little bit about NMR and then show you the results. NMR and more, I've named it. So this is the phase diagram of BKFA. It's a whole doped superconductor. Low doping level, there is a spin density wave. Then when we increase doping level, we have superconductivity with a maximum of 40 Kelvin at around 40% potassium doping, which then decreases when we increase doping even further. And then there's a change of the superconducting ground state around here. This is because there is a Lifshitz transition happening, and close to this Lifshitz transitioning, there was this dome of broken time reversal symmetry discovered by means of muon depolarization rate measurements. So this is the data right here, the muon depolarization rate. First of all, below this dome, you see that there is no change across the superconducting transition, which is here signaled by the susceptibility measurements. And we have this kind of multi-band wave pairing configuration. And then above this dome, again, across the superconducting transition, there is no change of the muon depolarization rate. And again, we can have this phase difference here of pi. But in this dome of broken time reversal symmetry, the muon depolarization rate is enhanced in the superconducting state, which is because of this special wave pairing configuration, which is a superconducting frustrated ground state. And of course, it has been discussed previously today, there is this enhancement of the muon depolarization rate already above TC, so here's the same picture zoomed in a little bit. So these critical temperatures are inverted, TC and TCZ2. And this goes together with the observation of a spontaneous nonce effect by Federico. And all of this goes together with this quartic-metal phase, which is governed by these four Fermion fluctuations. And which also belongs to this is that there is some pseudo-gap behavior observed in the specific heat, so there's an increase of the specific heat already far above TC, which is due to some to pre-pairing fluctuations in this material. And all of these critical temperatures have this field dependence right here, so it's all decreased in applied magnetic field, hinting this was like one of the main arguments against, for example, ferromagnetic order, which, for example, would be enhanced in magnetic field. Right. So now some people would still be arguing that this could also still be explained by conventional spin magnetic order, and therefore we decided to measure NMR because in the NMR we would definitely see some even low energy magnetic fluctuations. So let me quickly introduce to you NMR, because even though it's a very old technique, I regularly find that people are not too familiar with this technique. So we use the fact that some nuclei can have a spin, and therefore when we apply a magnetic field, we will have a splitting due to the Zeeman interaction, and these now non-degenerate eigenstates are occupied according to a Boltzmann distribution, and there the nuclear magnetization will precess around the applied magnetic field with the Larmor frequency right here. So this precession frequency depends on the applied magnetic field. Now we can manipulate this nuclear magnetization. We can, for example, invert it by applying a resonant high-frequency pulse. And this excites the nuclear magnetization. And after this high-frequency pulse, everything will relax back to its thermal equilibrium with a time constant that we call T1, the spin lattice relaxation time. And all of this will generate a spectrum this looks very smooth. In reality, it is never that smooth. There's always a lot of noise in there. And we are mostly interested in spectral properties. For example, the night shift, which is proportional to local static susceptibility. But also the dynamic properties, the spin-lattice relaxation rate, for example, probes lower energy excitations. And in principle, it depends on the density of states. Now, because I was measuring arsenic NMR, this picture is looks a little bit more complicated because arsenic is a free half nucleus, and therefore we have a fourfold degenerate eigenstate, which then, when we apply this magnetic field, is split into 4 states. The spectrum would look something like this without any interactions. Now, if we turn on, for example, nuclear-nuclear interactions, and just due to general statistics, we usually see a broadening of this line. And then, due to nuclear electronic interactions, there will be an additional shift of the NMR line. Now, because nuclei that have a spin that is larger than 1/2 have a quadrupole moment, they also interact with the crystal electric field, which results in even more complicated spectrum, so a splitting of the whole NMR spectrum, where these are the satellite lines and this then now the central transition, and the splitting of these satellite lines depends on the quadrupole frequency, so on the interaction of the quadrupole moment with the crystal electric field. In very simple schematics, the NMR setup can look something like this. Most important part here is the spectrometer, which generates high-frequency voltage pulses, which then are led through some components into the NMR resonance circuit, which can look something like this, which contains capacitors and the NMR coil in which the sample sits. Now these high-frequency voltages will generate a high-frequency field at the sample, which will penetrate the whole sample and then excite the nuclei in there. And the relaxation of the nuclear magnetization back to its thermal equilibrium will then generate a pickup signal that we then can measure. This is, okay, cannot perfectly see it, but this is how the sample looks like. So this is BKFA in there. They are very thin plate-like samples, and this is the NMR coil, so this one here, which is hand-wound. And important to know is that for an NMR experiment at any given temperature and field, the signal intensity depends also on the volume fraction of excited nuclei. So, for example, when the sample enters the superconducting state, we will see a decrease of intensity because we get shielding currents and therefore we don't excite all of the nuclei in the sample anymore. Right. With all of this, I can come to some first results that are not NMR, because here are some characterization measurements of exactly the sample that I measured. First of all, the resistivity, where you see that Tc is suppressed in applied magnetic field. And the specific heat, which importantly also shows the same behavior, that there is an enhancement of the specific heat at temperatures already far above Tc. And this is also, so I measured in the end at 8 Tesla. This is also seen at this field. So the pseudo-gap behavior is existent in this sample. And as you have seen, an important result for this whole topic was the spontaneous Nernst effect, which also appears here in this sample. We have to note that the Nernst effect cannot be, or the spontaneous Nernst effect cannot be resolved anymore at 8 Tesla, where I measured. You have seen in the morning that it's actually quite difficult to do this, to resolve the spontaneous Nernst effect. So it doesn't mean that there is no TCZ2 transition, which, for example, can also be seen in the specific heat, because there was this bump, as you remember, that can also be associated with the TCZ2 transition that we see here in the specific heat, and as I told you, the pseudo-gap behavior is existent here as well. Right, so now every time we want to do an NMR experiment with a single crystal, it is first important to orient the sample in the external magnetic field, and this we can do by already measuring the NMR spectrum, so the sample orientation dependent NMR spectrum. This is because the crystal electric field and the chemical shift are usually tensors. So from this spectra measurement we can extract the night shift, which you can see here on the right. We can fit this with a sine squared and then find the optimal orientation of our sample in the applied magnetic field right here. This is important because if you want to know something about quadrupole interactions, we have to be aligned optimally. Because next I want to discuss the bulk potassium doping that was first measured by XRD measurements and this known relation between the z-axis parameter and the doping level. So from this we know it's around 77%, but we can also determine the potassium doping, the bulk potassium doping, by NMR measurements. So here is a spectrum at 8 Tesla and 20 Kelvin, where this is the satellite, this is the central transition, and this is one of the satellite lines. And if we're now oriented, let's say almost perfectly, then we don't need to measure the splitting of the satellites, because the measurement of one of these satellites takes around a week or something. So for every measurement I show you have to keep in mind that NMR is a very long experimental method, so measurements take a while, so sometimes we don't have the luxury to investigate everything that we want, and we have to make do with what we have. So this is why we decide, okay, it's enough to measure one satellite line, because in the optimal orientation, so-called second-order quadrupole effects will not have an impact on the central transition, and therefore we can determine the quadrupole frequency, or the just by the difference or the distance between the satellite and the central transition. And now I compared our single data point here with previously known data from Hirano et al. Already measured in 2012. They see a linear dependence of the quadrupole frequency on the doping. And if I just plot my quadrupole frequency at this doping level that we determined, it fits very well into the overall systematic behavior. So with this we also confirmed the bulk potassium doping of our sample. And now I want to take a short detour and want to tell you what we can learn from the NMR and NQR line width, because usually when I present this topic, afterwards people are concerned, what about your sample quality, what about homogeneities, and so on. So I just want to show you what we can learn from the line width about our sample quality, let's say. So in general, the line width represents a distribution of internal hyperfine fields in our sample. And I can show you some data from this same paper, from the Hirano paper, where they measured NQR. And they see, so this is the NQR spectra, so zero field NMR you could say, where they see that the line width, first of all you see this shift that was also shown in the previous slide, but the line width is broadening in this higher doping regime, and then it's very sharp again for the pure potassium iron arsenic 2. And this was interpreted just as a random distribution of barium and potassium in the sample, which then leads to this line broadening here. And now you can keep in mind that this NQR line here, around 70%, is around 2 megahertz wide. And if we now go back to the line width of our satellite transition, you see it's also around 2 megahertz wide. And in general, you can say that the satellite line is broader than the NQR line, because usually for NQR line you only have one quantization axis of the EFG tensor, but for the satellite line you also have an additional quantization axis due to the external magnetic field. Therefore we can say that we have at least as good samples as they had back then. And yes, and what we can also learn from this spectrum already right here is how the quadrupole effects affect the central transition. Because if we are not aligned perfectly, it could be that, for example, the broadening of our central transition comes mainly from quadrupole effects and not from magnetic effects, or from nuclear electronic interactions. And if we just take into account the first order quadrupole broadening from the satellite line, and then calculate from this the second order broadening of the central line, I find that the line broadening is around 4 kilohertz. And if you compare this to the overall line width, you see that this is very small compared to the overall line width. So therefore, we can conclude that it's mainly governed by nuclear electronic interactions and not nuclear quadrupole interactions. Okay, with all of this in mind, I can show you some real, more important data, let's say, which is the temperature dependence of the arsenic spectrum. And first of all, you see that there is 2 components in the spectrum, which was quite puzzling for a long time, but thanks to STM measurements that you will, I think, also see later, you see that there is this nanoclustering, so this random distribution of potassium and barium in the sample, which can lead to these 2 spectral components. So these are just a result of potassium-rich and potassium-poor regions in the sample. And what you see is that this is, say, the case for the whole temperature range. We can now fit both all of these spectra with just a double Gaussian, and it fits really well for the whole temperature range. And then we can analyze these peaks individually. So now I want to just focus on peak B because it's sharper and honestly makes the data look nicer, but peak A has in general the same qualitative behavior. So let me start with what I just discussed, which is the line width. Remember, it's a distribution of internal hyperfine fields over the sample volume. And you see that there is no change over the whole temperature range. So Tc is around here, and I've already put in this T star, which will be clear where this comes from later. And Tcz2 is also in this temperature region. You see that there is no change of the line width. And if we would have some sort of static magnetic order which develops somewhere in this temperature region, you would expect there would be some line broadening, for example, or for example, antiferromagnetic order, a line splitting would be seen in the NMR spectrum. But instead, we see nothing, which already hints that that it's not that there is no static magnetic order in this region that we measure. Next, we can have a look at the night shift, which decreases monotonously coming from high temperatures and then flattens out here in this temperature regime. And then down here at Tc it has this kink. Maybe you're more familiar with night shift measurements because they're a little bit more famous due to Johnson gluconate. This is no spin triplet superconductor. Yeah, maybe also a nice result, but not very important. But we are not sensitive to anything with the night shift actually here in this temperature regime. The first interesting result, in my opinion, comes here for the temperature normalized intensity, which is, let's say, more or less constant at high temperatures. And then there's a very drastic slope change here around Tc. But in this temperature regime, it's very small to be fair, there's already a slight decrease of the intensity, which could already hint at some sort of pseudo-gap behavior, maybe due to some local screening, due to pre-formation of Cooper pairs. We are very bold to claim that. But since we were not...
Sorry, just for clarification. So this lines, this night shift and E of T, this is if you follow the A or B peak?
Actually, so this is A. Sorry, this is B.
Okay.
This is B, and this is for the intensity of the whole line, because it was easier to calculate. Okay, so this is just the numerical intensity of the whole line. Okay. So because we were not sensitive with the night shift, let's say, to this pseudo-gap behavior right here, we can have a look at the μSR night shift actually. So this is μSR spectra measured by Vadim on a sample which has a similar doping, 75% potassium doping. and here is and the night shift was determined by this peak position of this peak 1. And what you see is that in this temperature regime, it's pretty much linear. And then here, clearly above TC, so TC again signaled by the sudden drop of susceptibility, above TC there's already an increase or a decrease of the negative night shift, which hints at pseudo-gap behavior in the MUSR. Right. So this is, let's say, pseudo-gap evidence from static properties. Now, we also want to investigate the dynamic properties. This is why we, of course, measure the spin lattice relaxation rate. And here I want to show you, let's say, the doping dependence of the spin lattice relaxation rate, again from the same paper, where my data is the one in red here. And I would say in the overall systematic fits quite well with the previously measured data from already over 10 years ago. And what you see for, let's say, let's concentrate on these curves here, you see that there is a drop every time that we enter the superconducting state, which is also observed here in this data. For this 40% potassium doping, there's actually a slight increase beforehand, which might be due to some, let's say, remaining magnetic fluctuations. I know there's discussions how far the magnetic fluctuations in the system actually reach, if they're all suppressed when the spin density wave is suppressed, or if they even reach up until the Lifshitz transition. So this could still be some remnant magnetic fluctuations. And actually here, for the pure potassium iron 2 arsenic 2, you see that there's a very strong increase of the spin lattice relaxation rate, possibly because this is also already close to another magnetic instability. Right, but the important point is the overall data fits very well into the previously reported data. And now we can have a little bit closer look at this curve. So here I compare the spin lattice relaxation rate with the resistivity and with the specific heat, all measured on the same sample in the same field. And the first thing that you can see is that in this temperature regime, the spin lattice relaxation rate is pretty much constant, which is expected. It's called Coringa relation. And that there is a linear behavior, let's say, below TC here. We didn't actually measure towards lower temperatures due to some time constraints. Would have honestly been nice, but okay, we didn't. Important thing is also that we don't observe a Hebel-Stichter peak, which is, I mean, generally not expected to observe a Hebel-Stichter peak for unconventional superconductors, but it's also a result. The interesting result is actually this one here, where we see that there is a slight slope change starting around this T star here. So this is hinting at a pseudo-gap behavior coming from p-pairing fluctuations, which are necessary for the quartic-metal state to exist, let's say. And this goes together also with this enhancement of the specific heat right here. They happen at slightly different temperatures, which might just be due to the different sensitivities of the experiments. And something important that I have slightly touched on but have not mentioned in full yet, it is very important what we don't see in this curve. Because in the beginning I mentioned, okay, maybe all of the effects are still, could still be explained by some sort of low energy magnetic fluctuations. But if we had any of these in the system, you would definitely see some divergence of fluctuations here in the system. So the spin lattice relaxation rate should increase and should show some sort of maximum around TC if there were any magnetic fluctuations in this regime. But we see none of these, and therefore from an NMR from an NMR perspective, we can say that there is no magnetic fluctuations in the system. Which brings me already to my last slide, so we can put all of this together. Let's say extend the phase diagram a little bit. So we have this broken time loss symmetry superconductivity with the quartic-metal, again shown by the Nernst effect, all extended to higher fields. And then we can add the pseudo-gap temperatures. So these were extracted first from resistivity, where the pseudo-gap behavior is seen, from the specific heat where it's seen, and also from the NMR, where we also see the pseudo-gap behavior. And again, I want to maybe leave you with the most important point, I think, is that we have shown you that there is no magnetic order in the system, as we have shown by NMR. So with this, I'm already at my end. I was a little bit fast, but thanks for listening.